Now, the rate of disintegration of atoms, dN dt, that's how they decay with time, is proportional to the number of atoms present. That means a sample that has more atoms will have higher decay rate. Of course, I'm going to put negative here because that is decrement. Because as they are decaying, their numbers are decreasing. So the rate of decay is proportional to the number of atoms. So a sample with 1 billion atoms and a sample with a million atoms, their decay rate won't be the same. That of 1 billion will have higher decay rate than that of 1 million. So let's work a little mathematics from here. So we can say dN dt is proportional to negative n, and dN dt will be equal to negative k n. This is constant of proportionality. Okay. When I cross and multiply here, I have dN to be equal to negative kn dt. Then I want to divide both sides by n. So here is upon n, here is upon n. This n goes with this n. So dn dt, dn upon n equals negative k dt. Remember again that this k is constant of proportionality. So I'm going to integrate both sides. We can call this equation 1. So I'm going to integrate both sides of equation 1. Okay. When I do that, I'm going to have integral of dn upon n to be equal to, this is a constant, negative k integral of dt. All right. When you integrate dn upon n, that gives you ln n. So we are going to have ln n for this, and this will be equal to negative k. So when you integrate the t, you're going to have t. So have ln n equals negative k t. Exponent of ln n equals exponent of negative kt. Of course, after the integration, I have to include a constant as a constant of integration plus c here, constant of integration. All right, working it further, exponential in n now gives us n, and this is going to be exponential negative kt multiplied by exponential c. This is by indices. If we have number having two powers joined by addition, that means that was the same number repeated with the powers. All right, from here, we're going to look at some initial conditions when time is 0, so that we actually know the value, what this constant stands for. So at t equal to 0, that is initial time, we expect the number of atoms remaining to be n naught, which is the total number of the atoms in the sample. So at t equal to 0, we expect the number of atoms remaining to still be intact. That's a complete n naught. So we're going to substitute this and see. So that means n naught equals exponential negative k, substituting 0 here, then dot exponential c. So n naught will be equal to exponential 0 dot exponential c. So n naught will be equal to exponential 0 is 1, that is 1 times exponential c, and that gives us that n naught equals exponential c. So this exponential c corresponds to n naught, the total number of atoms in the sample. So we're going to substitute this n naught here into this place. Let's call that equation 2. Okay, so we're going to substitute this into this equation 2, and that gives us n to be equal to exponential negative kt dot n naught. That's this exponential c, we've gotten it as n naught. So n can be written as n naught exponential negative kt. Of course, some people use lambda for this constant. So you can write n to be n naught exponential negative lambda t. The choice is arbitrary. That means you can choose anyone for yourself. So this equation here governs radioactive decay. All right, one more equation will be necessary. One more derivation will be necessary. Now, this is the equation we have gotten for the decay. And like I said about this lambda, some people use lambda, some people use k. The choice of the symbol is arbitrary, but I think most people use lambda. So let's go by lambda. Okay. So let's look at this. Okay. At t equals half-life, let's look at this condition. At t equals half-life, use t half-life for half-life, right? Then n, the number of atoms remaining, will be n naught over 2. That's when the time corresponds to the half-life, the number of atoms remaining is going to be half of the initial number of the atoms. So we're going to substitute this and solve and see what we're going to get. So for n, we're going to put n over 2, n naught over 2. So have n naught over 2 equals n naught exponential negative lambda, then t half-life, because the time is going to be half-life when the remaining atoms is n naught over 2. So let's solve this equation and see what we have. All right. So we have n naught over 2 equals n naught exponential negative lambda t half-life. This n naught cancel this n naught. So we have 1 over 2 to be equal to exponential negative lambda t half-life. So let's take the natural logarithm of both sides so we can eliminate this lane. So I'll take lane 1 over 2, and that will be equal to lane of exponential negative lambda t half-life. This lane will cancel this exponential. So we have lane 1 over 2, which is lane 1 minus lane 2, law of logarithm. In logarithm, when you have division, that turns to subtraction. You just lane the numerator minus lane of the denominator. All right, this will be equal to negative lambda t half-life. Now, lane 1 is 0, so we have 0 here, minus lane 2 to be equal to negative lambda t half-life. And that gives us negative lane 2 to be equal to negative lambda t half-life. This minus here, strike this minus. So from here we can say lane 2 is lambda t half-life. And that gives us that t half-life is lane 2 all over lambda. And also, we can write lambda as lane 2 over t half-life. All right, this lambda here is called decay constant. Lambda is referred to as decay constant, as we have seen from our derivation. Even though in our derivation we use letter k, but now we switch to lambda. So it's still the same thing. So this is a connection between lambda and half-life. It's an equation connecting the two. Now remember that lane 2 is 0.693. So this is same as 0.693 over lambda. So take note of these equations. We're going to use them to solve problems now. Let's look at this example here that we're given. This question says, if the decay constant of a radioactive substance is this value, the half-life is dash. So we have gotten these equations, beautiful equations that we're using to solve all these problems. So let's solve this. Solution. First, we are given the decay constant, which is lambda here. So lambda is given to us as 0.231 per second. And we're asked to get the half-life, So we don't know half-life. So we're going to use this equation that connects lambda, and half-life. So we're going to say half-life, t half-life, is going to be ln 2 over lambda, which is going to be 0.693 upon lambda. Lambda is 0.231, and this will give us 3 seconds. 3 seconds, and that is option A. So option A is correct. So that is how you apply this formula to solve problems.